Good morning, physics. This is your electricity current subunit notes packet, Ohm's law. Voltage results in current flow. So the more voltage that is supplied, the more current can flow. Resistance opposes current flow, so it should make sense that the more resistance you have, the less current can flow. Now we're going to write down Ohm's law, and we're going to write it down actually two ways, solve for two different variables. The first is current equals voltage over resistance. And the second is voltage equals current times resistance. They're the same equation, just solved for the two variables that we most often are using it to find. Let's do some examples. A potential difference of 25 volts, and as soon as you see that number, you can stop, look at the unit, and that'll tell you that's voltage, so you write V equals 25 volts. It is supplied to a circuit with 100 ohms of resistance. Again, every time you find a number, you catch it, you tie it to the variable it belongs to, and write down your known information. And then you also have to catch the question, which is how much current flows through the circuit. So I equals question mark. We've already got Ohm's law, and it's solved for current. So this is me just filling in the variables there. We don't have to worry about wondering what the unit is going to be here. We know that current is measured in amperes. And once I am satisfied with the way my highlighter is looking, we'll move on. Example 2. A current of 2 amperes flows through a 10 ohm resistance. What voltage must be supplied to this resistance? Again, every time you see a unit, you use it to tell you what variable you have and collect all your variables. Then you also have to catch what the actual question is. What voltage must is going to indicate V equals question mark. We already have written down the equation, solve for V, so we can just fill in our numbers. This is an easy calculation. 2 times 10 is 20, and we're solving for a voltage. Our unit is in volts. Example 3. A 10-volt battery establishes a current of 5 amperes in a circuit. What is the resistance of this circuit? Your voltage is 10 volts. Your current is 5 amperes. And the question is, what is the resistance? So R equals question mark. Now we do not have the equation solved for R, so we're going to have to fill in variables and then solve for R. You have 5 times R in my example here, which means you want to move the 5. So you're going to have to divide both sides by 5, and that'll give you 2 ohms of resistance. Here are some common circuit elements that we need to know. This is a cell. Your positive terminal is always the longer side, and your negative terminal is always the shorter side. When you have more than one cell, we call it a battery. These next two also are similar looking. The first is your resistor. The second is a potentiometer. This is a voltage divider, and we'll learn more about this element and its applications later. This is your light bulb. There is an alternative symbol, because there always is, that you will sometimes see. It's this X, and that stands for lamp, which is an older way to say light. We've seen the switch symbol before. We'll just specifically say that this one is open. Now we're going to talk about 2 meters that we use to measure quantities in a circuit, the voltmeter and the ammeter. The voltmeter measures potential difference, and the ammeter measures current. The resistance of the voltmeter has to be high. If you want to accurately measure potential difference, you do not want to have current going through the meter. You want it going through the component so that you can measure around the component accurately. When we measure across a component, we call it being parallel to the circuit. The ammeter, on the other hand, we do want all of the current to flow through it so that we can measure it. So it goes into the circuit and becomes a part of the circuit in what we say series in the circuit. Let's take a look at proper use of meters. So here we have a battery. It is a 5-volt battery, and a resistor, a 2.5 ohm resistor. I'm going to mark the positive and negative sides, and we'll note that current will flow in the same direction that a positive test charge would move, and so it's going to be going clockwise. Measuring voltage across the battery should be obvious to you. It's going to measure a potential difference of 5 volts. However, here, if I measure the voltage, the potential difference is 0. Here, if I measure the voltage, this is the only component in the circuit. So this is where we're going to use our 5 volts, and the drop will be 5 volts. And again, here, we're not measuring across any component. It's going to be a potential difference of 0. I almost wrote current there instead of ammeter. Ammeters are going to be in the circuit. How are we going to know what the current is? Well, let's use Ohm's law. The total current equals the total voltage over the total resistance. We know that's going to be 5 over 2.5. So the total current is going to be 2 amperes. And the reason for showing you this is to tell you that in a series circuit here, the current is going to be the same everywhere. So if I measure on one side or the other side or anywhere else, I'm going to measure a current of 2 amperes. If I have to record this power section one more time. Moving electrons, current, requires energy. Do you remember? Energy is work. Work is the change in kinetic energy. We measure that in joules. We've also seen power before. We measure that in watts. So let's talk about power in a circuit. How much energy gets used depends on the strength of the push, voltage, and the rate of flow, or current. So power is going to equal current times voltage. The rate of flow here, I'm just reminding you that current is a rate, I equals charge per time. Here I'm going to replace each of my current or voltage variables so that if we have some other variables, we can still solve for power really easily. And I'm going to do that by Ohm's law. I just replaced there current with V over R. So that's actually V squared over R. If I have voltage and resistance, I can use this equation instead. Same thing. I'll start at P equals IV, but V is equal to IR, so that's I squared R. So here I just solved for some different variables to give us an easy starting point. All of these are true, all of these are equivalent, they're all equal to power. It just depends on what variables we're given and what we're trying to solve for. P equals IV is the major one that you should memorize. Example 1, a 12-volt battery is connected to a circuit which allows 10 amperes of current to flow. What is the power of this circuit? You find your numbers, you're writing down your variables that you have. This is our basic one, just confirming that we can put the numbers in correctly to solve for power. 10 times 12. This is going to be 120, and power is in watts. We'll say W for watts. Example 2. A 100-watt light bulb is connected to a 120-volt power supply. What amount of current must pass through the light bulb? Power is 100 watts. We were given 120 volts, that's a voltage, and the question is what amount of current? So that's your I equals question mark. We're going to fill in what we know. This is going to be a use of the multiplicative inverse because we are going to divide both sides by 120 in order to move it to the other side of the equal sign. And this is just me, I'm not using a calculator, I'm just reducing this fraction down. So 5/6 of an amp. Example 3. A 2 ampere current passes through a circuit with a 300 ohm resistance. What is the power generated in this circuit? A 2 ampere current. I see 2 amperes and I say, I equals 2A. 300 ohms means R equals 300 ohms, and I am looking for power. And so this is showing that it is worth it to have these other equations handy. We're going to go straight to power equals I squared R because those are the two variables that we have, and we can fill them in. That'll make it 2 squared times 300, or 4 times 300, or 1200 watts. A while ago, when we learned about power and work for the first time, there was an equation that related them to each other, and it was power equals work per time, because we defined power as the rate at which we do work. W equals P times T is just a rearrangement of that equation. And in fact, we have some other pieces here of equivalent statements. It just depends on what variables we're given, and we can set any two of those pieces equal to each other. Let's practice. We've got a 200 watt heater. I see 200 watts. I'm going to stop. I'm going to write down P equals 200 watts. It's run for 5 seconds. The voltage is 110 volts. And they are shouting energy at us in caps to remind us that this does refer to work. It's a little more tricky to remember that one because it's a different word. We're just going to use work equals power times time. We're going to get 100 joules. Calculate the current passing through the heater. So this is giving us a new thing. Current is question mark. We can use any of the equations we've found so far, as long as we have the other two variables. If we use P equals IV, we do have the power, we do have the voltage, and we'll use the multiplicative inverse to move 110 to the other side and solve for current all alone, and you will get 1.82 amperes. A2. There we go. 1.82 amperes. Ta-da! Calculate the heater's electrical resistance. So now we keep solving and getting answers for new variables, but then we're asked for newer ones. I'm going to use Ohm's law for this. I'm going to fill in my current, which I just solved for, and my voltage, which I was given just in the beginning of the problem. I'm going to first move R to the numerator by using the multiplicative inverse, and then I'm going to divide both sides by 1.82. I know that there is a few different ways to do it. I'm doing it this way because it seems to help some of my students. You're going to get a resistance of 60.4 ohms. What am I doing? Oh, I believe I was showing you here that you can use and set any two of those pieces equal to each other. So if you saw a different relationship, for example this one, and wondered why I was using a different equation, it doesn't mean you're wrong. We can fill in things that we know into this equation too and still solve for R, and we're going to get the very same thing. It might be a little off if you do this calculation. If that happens, it's because of rounding errors. And that will happen when you break your calculation in your calculator into several steps. You should memorize P equals IV and Ohm's law, which is I equals V over R. If you don't have access to any other formulas, these two will help you get all of the pieces that you need to set equal to each other. And so that's what I'm purposely doing in this question. I'm not jumping straight to the relationship between P, R, and V. I'm solving for current using Ohm's law because I have voltage and resistance. And then I'm putting that current with the voltage into P equals IV to solve for power. And I'm doing this instead of doing P equals V squared over R from our former equations page to show you that it's the same. It'll come out the same. It'll be 0.18 watts, no matter which way you do it. Number 3 is going to ask several questions about a toaster. A toaster with an internal resistance of 11 ohms is connected to a 110 volt source of electrical potential, a standard outlet. A. Calculate the power used by the toaster. All right, we're going to start collecting some variables that we have. So we have resistance and voltage given. And first off, we're solving for power. This is the same exact one from the last question, so here we'll go straight to P equals V squared over R. These two pieces equal each other, and we can fill them in. We'll get 1100 watts. Now that we have that information, we'll continue on to B with that. How much energy is used by the toaster if it takes 1 minute to produce a slice of toast? Energy is work, and one great thing about writing down all of your variables is you'll catch right away when you are in SI units. Here I stopped because I realized that minute wasn't going to work in my formula, so I converted it over to seconds before even going over to the formula. Work equals power times time. And this will come out correctly only if I have my SI unit of 60 seconds in there. And that'll give me 66,000 joules. C. Energy usage in the home is calculated in kilowatt hours rather than joules. If 1 joule equals 2.78 times 10 to the negative 7 kilowatt hours, what is the energy from B in kilowatt hours? All right, this has a lot happening, but the only important thing is we have a conversion. 1 joule is 2.78 times 10 to the negative 7 kilowatt hours. That's a ratio that equals the number 1 because they're equal, which means I can multiply my 66,000 joules by the ratio and not change the value. Which order should the ratio go in? Well, joules, the unit, needs to go in the denominator, so it cancels out the joules that I have in the 66,000 joules. And kilowatt hours has to go in the numerator because I'm going to kilowatt hours as a unit. When I do this calculation then, it's just a straight multiplication, and I'm going to get 0.018 kilowatt hours. If the typical cost for electrical energy in New York State is 14 cents per kilowatt hour, and I have never seen it written with the cent sign in front, how much does it cost to make a slice of toast? Well, I know that it's going to be 0.018 kilowatt hours times 14 cents, and it's going to cost 0.257 cents for a single slice of toast. How many slices of toast can you make for a penny is the last question. So it's going to be 1 cent a penny. And how many times can we fit this 0.257 into it? Well, that's 1 cent divided by 0.257 cents. And we're going to assume that you aren't going to exactly toast your bread the same exact way every time. So we'll approximate it and round it to 4 slices. The next video will be the last 2 sections of the notes packet, series and parallel circuits.